On November 4, 2010, at Changi Airport, Singapore, the giant Airbus A380 aircraft was quietly being refueled in preparation for the next leg of its journey from London to Sydney. With its massive size and sleek appearance, the A380 quickly drew the attention of a large number of passengers at the airport. However, just half an hour later, a serious incident suddenly occurred. One of the aircraft's engines suffered a major malfunction, leading to severe, uncontrollable damage. Fragments from the engine turbine were blown out as if it had exploded, damaging several of the aircraft's critical systems. At that time, 440 passengers were facing a life-or-death situation, all because of a manufacturing error. Smaller than a millimeter, a seemingly harmless mistake forced the flight crew to deal with over 100 technical alerts, along with the risk of a fire or explosion that could happen at any moment. Today, I'm going to tell you the story of an accident that nearly became the most catastrophic aviation disaster in history, the incident of Qantas Flight 32, operated by Australia's national airline. Mention the Airbus A380, and many people will immediately recognize this double-deck aircraft, the longest passenger plane ever built, with a colossal weight of up to 1.27 million pounds, a length of over 236 feet, and a maximum capacity of 853 passengers. The A380 stands out not just for its elite design, but also for the superior flying experience it offers. To operate such a giant, the A380 is equipped with 4 powerful jet engines to ensure maximum safety for each flight. The main character in today's story, this very first A380 owned by Qantas, was named Nancy Bird Walton in honor of the pioneering female pilot, the first female pilot of Australia. Moreover, this was also a tribute to her and her late husband. That morning, Qantas Flight 32 landed in Singapore after a leg from London. After a short layover, the aircraft prepared to depart for its final destination, Sydney. At the same time, the flight crew was also rotated. In addition to Captain Richard Champion de Crespigny, 4 other pilots joined the journey. This time, although regulations require only 3 pilots to operate an intercontinental flight, there were 5 on board this time, including a training instructor monitoring the captain's flight and a senior examiner evaluating that instructor. The flight crew had a combined total of 140 years of experience and over 71,000 flight hours, making them one of the most capable pilot teams ever assembled. And what they did next would prove they fully deserved the title of an elite flight crew. At 9:56 a.m. local time, QF-32 officially took off. Captain Crespigny pushed the throttle forward, and the aircraft, weighing 1,023,000 pounds, began to roll, accelerate, and lift off the runway. In under a minute, it gracefully ascended into the sky over the Singapore Strait. After takeoff, the captain switched to autopilot mode. The aircraft began following its designated flight path, continuing to gain altitude. All the indicators on the control panel showed that everything was functioning normally. To the flight crew and passengers, this was just another routine flight. However, few could have guessed that a technical error of less than a millimeter in one engine was silently threatening the safety of the entire flight. And just 4 minutes after takeoff, the aircraft reached an altitude of 2,133 meters, equivalent to 7,000 feet. 2 loud explosions rang out, marking the start of a tense and breathless period. Before the crew could recover from the shock of the explosions, the cockpit was flooded with a series of continuous warning signals. What could cause a modern aircraft, operating normally, to suddenly plunge into crisis in just minutes? Before we dive into the sequence of events, let's first understand the Trent 900 engine, the heart of this Airbus A380. Initially, this engine line was developed by Rolls-Royce to be equipped on the Boeing 747X. However, due to lack of market interest, the 747 upgrade project was temporarily halted. At that same moment, Airbus was seeking an engine solution for the A380 project. Rolls-Royce immediately proposed the Trent 900, which then became one of the official options for the super jumbo double-deck aircraft. Like many Other turbofan jet engines, the Trent 900 is composed of four main sections: fan, compressor, combustion, chamber, and turbine, arranged front to back. Structurally, it includes an inner and outer duct. When the plane operates, the front fan spins, drawing in a large volume of air. A portion of this air flows through the compressor and then into the combustion chamber, where it mixes with fuel and ignites, producing hot, high-pressure gases. This stream of gas spins the turbines, which in turn power the engine. In particular, the low-pressure turbine drives the front fan to continue rotating. The Trent 900 engine has a bypass ratio of 8.50 to 8.7, meaning most of the air passing through the engine does not go into the combustion chamber, but is pushed directly out the rear through the outer duct, generating the main thrust. The distinctive feature of the Trent 900 foot, compared to other engines, is that it includes an intermediate stage, featuring a mid-pressure compressor and mid-pressure turbine located between the high-pressure and low-pressure sections. The mid-pressure turbine consists of small rotating blades, driven by high-pressure hot gas, and transfers energy back to the mid-pressure compressor via a drive shaft. However, to keep all components running smoothly at high speeds, the bearing and lubrication system is absolutely essential. From the moment the engine starts, oil is continuously pumped through a network of tubes circulating around the bearings to prevent wear and overheating. Ironically, just 1 minute after takeoff, the lubrication oil pipe of engine number 2 on Qantas Flight 32 ruptured. The high pressure caused the oil mist to spray into the outer bearing chamber, where the temperature had already reached 707 degrees Fahrenheit, while the oil's flash point was only around 536 degrees Fahrenheit. The oil ignited immediately. The flames quickly burned through the front oil seal, spreading into the low-pressure region of the bearing compartment. Worse yet, hot gas from the high-pressure turbine entered this area, turning the fire into a torch-like glow. Soon after, the rear oil seal also burned through. The fire directly damaged the actuator arm that links the intermediate turbine disc to the power transmission shaft. Due to the extreme temperature, the actuator arm snapped off, causing the turbine disc to lose its connection and spin freely at incredibly high speed. Just 4 seconds later, the shattered into 3 large pieces, releasing an enormous centrifugal force, like a small explosion inside the engine. These fragments tore apart the rear section of engine number 2, punctured the fuel tank in the left wing, and caused fuel leakage. Moreover, over 650 electrical wires, functioning like nerves that transmit signals between various electronic systems on the plane, were also severed. Meanwhile, modern aircraft rely entirely on electronics to operate, from hydraulics to control systems. Flight control electronics, engines, and even landing gear were all operated through electrical signals. Though only one engine failed, the other 3 were still functioning. But with the control disabled, the aircraft was like a body that could no longer move on its own. The threat of a freefall loomed before their eyes. The situation had now become truly critical. On November 4th, 2000, giant Airbus A380 with 440 passengers on board suddenly faced a serious malfunction caused by a tiny manufacturing error, less than a millimeter. After 2 loud explosions inside the aircraft, the captain immediately understood that they were facing a potentially catastrophic situation. Without hesitation, he switched the flight mode to manual control to bring the plane, which was still climbing, back to level flight. All 5 pilots immediately focused all their attention on the aircraft's monitoring system, ECM. Within just 20 seconds, over 80 alerts at different severity levels simultaneously appeared on the control panel. The highest priority warnings popped up first, and all of them were related to engine number 2. After pinpointing the issue, the captain immediately pulled the throttle for engine 2 back to idle. As expected, the ECM system confirmed that engine number 2 had caught fire and shut down. Following standard procedure, the crew activated the first fire extinguisher bottle, but there was no response. They then activated the second bottle, but still no indication of fire suppressant release. This was one of the many consequences caused by the severed control wires. The fire suppression system had been completely disabled, and the situation didn't stop there. The flight crew continued to receive numerous warnings unrelated to the engine. The captain immediately realized they were now in an extremely critical situation. The first officer issued a pan-pan call, an urgent alert just below Mayday, to air traffic control. At this point, they were forced to face a critical decision. Should they make an emergency landing immediately or first resolve the technical issues thoroughly? Thanks to his experience, the captain realized that the autopilot system was still functioning perfectly. That meant the aircraft could remain airborne, allowing the flight crew time to gradually handle over 80 remaining ECM alerts, while also reducing the plane's weight by burning off fuel. This was crucial for a safe landing. The captain knew that landing without fully understanding the plane's condition would be extremely reckless. They still didn't know whether the flaps could deploy, whether the brakes were functional, or if the aircraft's control systems were still accurate. With so many uncertainties, the most reasonable course of action was to troubleshoot every alert and ensure that all crew members fully understood the aircraft's damage before attempting a landing. The turbine explosion fragments had destroyed the control wiring for all three remaining engines. Engines 1 foot and 4 switched to degraded protected mode, while Engine 3 operated in alternate mode. Fortunately, these engines weren't mechanically damaged. Only their electronic control connections were lost. After a full systems assessment, the crew agreed that the aircraft was still safe to continue flying. The first officer requested clearance to enter a holding pattern to circle around Singapore, buying time to address all outstanding ECM alerts. Once they had full knowledge of all the damage, they would proceed to land at Changi Airport. Inside the cabin, the loud explosion caused many passengers to see that the left wing had been punctured, leaking fuel. The lead flight attendant attempted to contact the cockpit using the emergency call system, but the weak audio signal and poor visibility of the call light made it difficult for the flight crew to receive the alerts from the passenger cabin. Fortunately, this situation did not pose an immediate safety threat. Shortly after, the second officer was sent to inspect the aircraft's exterior. Unexpectedly, a passenger who was also a Qantas pilot called him over. The man had been monitoring the exterior camera feed through the in-flight entertainment system and noticed that the left wing was leaking fuel severely. The officer immediately went to the aft lower compartment to confirm and witnessed the fuel streaming from beneath the wing near engine number 2. He quickly returned to the cockpit and reported the entire situation to the captain. Upon learning that a passenger could see the damage from the cabin, the captain decided to make a public announcement to reassure everyone. Ladies and gentlemen, I'd like to apologize. I believe you've noticed that engine number 2 has experienced a technical issue. The entire flight crew is working hard to manage the situation. The aircraft remains safe. We will continue to circle for a while longer and will begin dumping fuel to reduce weight before landing. After delivering this message, the captain added, "We need to complete a few mandatory checklists. I believe you will no longer continue to Sydney. We are now returning to Singapore. As soon as we have any updates, we will inform you." Immediately, the aircraft is still flying safely, and if we have further information, we will provide it in a timely manner. However, after turning off the intercom, the crew began to worry that passengers might panic upon seeing live footage from the exterior camera, which showed the left wing punctured and leaking fuel. After a brief discussion, they concluded that suddenly turning off the live feed might cause passengers to panic even more, or assume the plane was in more serious danger, was completely out of control. So they decided to keep the camera running as usual. Meanwhile, at Qantas's operations center in Sydney, the monitoring team detected an anomaly from satellite data sent by the aircraft. A dispatcher used the ACAR system to send several support messages to QF-32. At the time of the incident, the plane was flying over Batam Island, Indonesia. Several engine parts, including turbine discs and outer casings, had fallen into residential areas, damaging local homes. Luckily, most residents were at work at the time, so there were no. Locals photographed the debris with the Qantas logo and posted them online. Unverified Information spread quickly, leading many to mistakenly believe that a Qantas aircraft had crashed. The rumor quickly reached investors, and the Qantas CEO received a call asking why the company's stock price was dropping. That was the first moment he learned that his airline was facing a major in-flight emergency. After flying in a holding pattern for 50 minutes, the flight crew had completed all the technical procedures they could carry out midair. However, due to a fuel leak in the left wing, the fuel levels between the two wings became severely imbalanced. The planned fuel dump. The aircraft was now over the maximum landing weight limit, making the landing more urgent to minimize long-term risks. According to regulations, before any emergency landing, pilots are required to calculate landing performance to determine whether the aircraft can come to a complete stop within the available runway length. Changi Airport has 3 runways, with the center and east runways offering the greatest usable length. At 4,000 meters, the flight crew decided to choose the center runway because it was closest to the fire station, an essential factor in case of an emergency rescue. However, when they entered the data into the landing performance software, including current weight, at the maximum level and 9 failed systems, the software was unable to generate any result. The flight crew was stunned. No one expected the software to return an unable to compute error. They immediately took out the third backup laptop on board to try again, but the software still couldn't calculate the required braking distance. This situation was like a hidden warning. Even a 4,000-meter runway might not be enough to safely bring the aircraft to a stop. In reality, the reason the software failed to give a result was due to a design flaw in the system. Specifically, when multiple failures are entered at once, the software adds up all the correction factors corresponding to each malfunction. These numbers, when accumulated, caused the theoretical braking distance to exceed 4,000 meters. The value went beyond the software's processing capacity, preventing it from displaying a result. The calculations showed a braking distance so long that the software couldn't display the output. At this point, experienced pilot David Evans came up with a different approach. Instead of using the default maximum landing weight, he entered the actual current weight of the aircraft. Surprisingly, this method caused the software to bypass the multiplier mechanism for fault factors and return a result. To come to a full stop, the A380 would require about 3,900 meters, just enough, 100 meters shorter than the 4,000-meter runway at Changi. In the entire Singapore area, no other airport had a longer runway. Therefore, this was their only chance to land safely. After completing all approach procedures, the captain, Chris Crespigny, disengaged the holding pattern, and under air Qantas Flight 32 began approaching runway 20 center. During the approach, the captain turned off autopilot and switched to manual control. He quickly noticed that the aircraft's pitch response was slower than usual, but fortunately, the other control surfaces were functioning normally. Worried that the fly-by-wire system might affect the engines, especially engines 1 and 4, located on each wing, the captain decided to keep the outer engines at fixed thrust and only use engine number 3, the most stable one, to control speed. At the same time, the first officer informed air traffic control that the aircraft needed immediate support from fire trucks and requested an extended final approach to provide more time in case of hydraulic failure. Due to a loss of the blue hydraulic system, the crew had to use the alternate landing gear system. Fortunately, the gear still deployed properly. However, because the leading edge slats could not deploy, the plane could only use the trailing edge flaps to increase lift. This reduced the margin between stall speed and approach speed to just about 37 miles per hour. If they flew any slower, the plane would stall. If they flew faster, they risked overshooting the runway. Crespigny had to make extremely precise adjustments as the aircraft descended to 800 feet. He fully disengaged all automation. Each foot of descent brought more pressure as turbulence increased. With only one engine regulating thrust, the pressure on the pilot's shoulders was immense. Right before touchdown, a stall warning flashed briefly, but thanks to experience and composure, the captain successfully landed the massive Airbus A380 on Changi's runway. When the 952,000-pound aircraft touched down, Crespigny immediately applied the brakes and activated reverse thrust from engine number 3, the only one still operable. Although reverse thrust wasn't enough to slow the plane significantly, it helped reduce friction and brake wear. When the aircraft decelerated to about Chris Crespigny knew they had made it. He even turned on the cabin speaker and joked with passengers, "Ladies and gentlemen, welcome to Singapore." It is currently Wednesday, November 4th, 2010, 11:45 a.m. I think, like me, you all feel this was one of the best landings we've had in a while. The massive A380 stopped just 492 feet from the end of the runway. Immediately, fire trucks rushed in and sprayed foam onto the brakes to prevent fires from leaking fuel. While preparing for evacuation, the crew discovered that Engine 1 wouldn't shut down because the control cable had snapped. After confirming there was no fire risk, they decided not to deploy the emergency slides to avoid injury. With fire crews, the pilots had to use a personal phone to call Changi Ground Operations and request a staircase to board the aircraft. Inside the hot cabin, 440 passengers had to wait 50 minutes before being safely evacuated from the right side. Engine 1 continued spinning for more than 2 hours, even after being sprayed with water by fire crews. Nearly 2 hours after takeoff, all 469 souls aboard Qantas Flight 32 had safely returned to Singapore. No one was injured. This time, the news spread across the globe, but instead of panic, people breathed a sigh of relief. 5 pilots, through each decision under extreme pressure, achieved the best possible outcome. However, this incident also raised questions in the aviation industry about the safety of the Airbus A380. After 3 years of investigation, the official report was released. The cause began from a segment of the oil pipe that was improperly manufactured. Specifically, the pipe wall thickness was below standard, less than 0.02 inches, and the flare hole for the oil filter was off-center due to misaligned clamping. Critically, this defect went undetected after the pipe end was sealed. As a result, the faulty pipe was installed in multiple Trent 900 engines, including the even more concerning, the engine that exploded on Qantas 32 was not the most severely defective unit. Had it not happened on this flight, a disaster could have struck another. The consequences might have been far worse. After the full truth was uncovered, all bearing housings made by Hanno, the company that produced the faulty oil pipe, were removed from production and completely destroyed. Rolls-Royce also revised its design and manufacturing processes to ensure that from the initial design stage, all technical standards are clearly defined and strictly monitored with subcontractors. Even a tiny deviation, less than 0.02 inches, seemingly harmless, nearly caused the world's largest commercial aircraft to crash midair. But from that mistake, Captain Richard Champion de Crespigny, who demonstrated extraordinary composure, logic, and courage, was awarded the Australian Cross of Honour, a symbol of exceptional achievement and service beyond measure. Not only him, the 5-foot pilots of Qantas Flight 32 were also honored with the 2011 Polaris Award, the highest honor in international civil aviation. In this near disaster, the design and technology of the Airbus A380 were rightfully recognized. Even though one of the 2 hydraulic systems failed, the advanced electronic control system still enabled the aircraft to maintain effective flight control. The autopilot system continued functioning smoothly while the ECM system, along with detailed status displays, helped the crew maintain constant and accurate awareness of the aircraft's condition, allowing them to make the right decisions, never letting panic waste precious time. All of these factors helped the crew hold on to complete trust and preserve life itself. For the airline, Qantas, this incident further solidified an unshakable tradition. If it can be fixed, it absolutely won't be discarded. That very Airbus A380 foot was fully restored after 2 years of repairs. At a cost of $139 million. It was successfully brought back into service. And as of today, the Nancy Bird Walton, the aircraft named after Australia's first female pilot, continues to soar safely along its familiar route from London to Sydney.